Hello, it's Brian Kinghorn again, and I'm bringing you an overview of MateSel with a bit more detail than you saw in the general introduction. We're going to do a test drive of the demonstration project using the Windows desktop version. And just to remind you that MateSel is essentially an integrating framework where all the different issues that are of importance to animal breeders are pulled together and analyzed together to give a mating list, which is the outcome. And that mating list incorporates decisions on selection, matings, collection of embryos and semen, movement of animals, and so forth. And also to remind you that the practitioner, the user, yourself, that person is involved in driving the analysis to bring expertise and experience, attitudes and desires into the analysis to give some ownership of the actions taken, which is the mating list that I did describe. So let's start with the Windows desktop version. Having logged in, we click the open icon to open the MateselClassicDemo example which we're using. And as you saw in the general introduction, there is a bit of information about that file given initially, and we can go into that in more detail. If we click run, we get the console showing us the numerical progression of the analysis, and the frontier graphic over here on the left shows us the results graphically for the two key components, which is progeny index and parental co-ancestry. And we always want to have high genetic merit in the progeny, and we always want to have high genetic diversity in the population. So we want to tend to be towards the left and upper side. Now, the first thing that MateSel did was to draw this frontier, which shows the limits of how far you can go in each direction. And we're currently using a balance strategy, hard constraint and target degrees. And that means our policy is reflected by this 25-degree line here. We want to go as far up that line as we can. So 0 degrees gives us the maximum genetic gain. 10, 20, 25, and up to 90 gives us the maximum genetic diversity. So if I click on print matings, and look at mate selections, I can see the matings that will be made to reflect the solution that is here. And if I click show sire use and sort on uses, we can see that Wayne is the most used sire, and he's used to the limit that we've got set in this simple example of 25 uses. So let's change our target degrees to give maximum genetic gain. If we update that, we see the evolutionary algorithm rather quickly take us up to that optimum. I click the update button on the bottom right here, and we can see that Magnus and Wayne are used the maximum permissible number of matings each, 25, giving us the 50 matings that we are asking for in this analysis shown here on the input. Let's now go for maximum diversity, which is 90 degrees. And if I click update, even before it's settled down, we will see that there is a much larger number of sires used to give more genetic diversity. We still have 50 matings, and we see that some sires are used more than others, which may be surprising, but of course majority here is the most lowly related sire to the rest of the population, and he's most new blood, if you like, and therefore he gets more matings than others. So let's go back to 25 degrees. That's given you a feel for balancing these two things, or genetic gain and genetic diversity. And what we do is, if we bring in another issue, let's look at trait management. These are the distributions of predicted genetic merit in the progeny. The black tick for yearling weight here shows what would happen with random mating amongst the candidates, and the red tick is the current solution and is higher than the black tick, reflecting the fact that the index is pushing yearling weight upwards. Let's say we want yearling weight to go a little bit higher, which may or may not be a good idea, but if we click in this graph, we could click increase mean, but I would always direct you to have more control and go for tactical desired gains upwards. There's a grey line appears on the graph here. If I click over on this point, that's at an equivalent of 111 EBV units. So if I click invoke, that will turn red, and if I resume, then the analysis is giving us a solution which ensures that we've got at least that amount of merit for yearling weight, and there is a small compromise here, balanced compromise between genetic gain and genetic diversity, which the target degrees does. and we might think that we would probably want even more yearling weight. So let's say we go and say that we want to have, click a bit further to the right and say that we want to have that amount of gain in yearling weight. The analysis may or may not get there depending on a couple of things. It hasn't quite got there. I'll push that a little bit harder by putting the weighting up to 10. And it does manage to get there, but at great compromise, really. So we do have what we asked for in yearling weight, but at a big compromise in both genetic gain and genetic diversity. So we would probably bring back our desires a bit here. But while I'm sitting down here looking at the compromise that we have made from the frontier, let's now consider a different way of achieving such a compromise by looking at a hard constraint on co-ancestry. So if now we were to take co-ancestry approximately equal to this point in the frontier, which is about 0.8, let's just try 0.8, 0.08, as a limit on co-ancestry, and I update. And you'll see that the limit is brought over, and now what MateSel is doing is giving us the highest possible genetic gain, given this constraint on yearling weight, and given that we will not step over to the right of this green line, which is our limit on co-ancestry. To me, it seems more reasonable that rather than make all the compromise in genetic gain, you would probably go for a policy of a hard constraint and target degrees in preference, and balance, get a little bit more gain at the cost of a bit more diversity. That's a choice you have to make. Now we're going to have a look at a different type of constraint. So if I take this one off by clicking on the yearling weight graph, click on invoke, that's maintained our minimum value desire. If I resume, we'll now make it back to the frontier because I've pulled off this constraint. And let's look at intramuscular fat. And if I click there and say I want to go for bimodality, target bimodality, I now get two lines that I can work with, one with a left click, one with a right click. So let's say that I want to have bimodality around these two modes. I could enter numerical values for them up here, which I won't do in the interest of time. Let's say we want 30% in the upper group. I click invoke. When I click invoke, you can look down here, you'll see that these grey lines turn to red. And if I click resume, then we are getting that bimodality at some compromise. And we could get a stronger level of bimodality if we put the weighting up. And all weightings in MateSel are set so that a value of 1 tends to give you a reasonable sort of starting point to go from. This might be too much compromise. You notice that we are to the left of the target degree lines. We're still legal. Let's say we want to put that weighting down a bit. Let me put it down to 0.25. We tend to make quite big changes in weightings to get a reasonable effect. So you'll see that the bimodality is probably softened a little bit, and we're much closer to the frontier. So that might be a judgment we make. So we might have in the lower arm, we're probably looking for producing bulls to sell to the domestic market with low intramuscular fat, whereas a smaller market for bulls that we want to send off to clients who are breeding for the Japanese or Korean market with higher intramuscular fat. So that's a reason why you might go for bimodality. So I'll now switch off that bimodality by unclicking the invoke check button. And just look at a couple more things rather quickly. Marker management, we won't do anything with now, but we do have the same way of managing outcomes there. So in this bottom row, I could be reducing the probability of having genetic defects and organizing mating so that you have less chance of that happening. I won't do that now. We'll go over to progeny inbreeding. The red line at the bottom tells us average inbreeding coefficient in progeny, and the green line tells us the inbreeding coefficient of the most inbred mating. So let's just put a weight on progeny inbreeding. I'm going to make it -1. As I've suggested, these things can go on that sort of a level. And -1 is a good value to have by default. You can see that compared to what is essentially random mating of selected individuals, we've had quite a decrease in inbreeding in the progeny, no compromise in this case on the frontier. The reason we get no compromise is because the same selections are being made, most likely, with the same number of matings per individual, we're just juggling the mate allocations to give a better outcome here. Whereas if I were to increase the weighting, let's do it dramatically, which is one way of doing these things in MateSel, so something really happens. If I click update, we'll see that the inbreeding starts to come down even further. And when that happens, we start to get more compromised, because now we are changing which animals are selected, as well as the pattern of mate allocation, in order to bring it down. But in actual fact, we have to put a very strong weighting on and really give incentive to, let's just do this, really give incentive to the program to reduce inbreeding. And here it's just going hell for leather for reduced inbreeding progeny, and it's a stupid result. You will find that having a value of something like -1 will tend to give you a much more reasonable result. It's there for you to play with and find out the properties for your own data set, as is indeed the case for any of these things we look at. It's worth spending time doing research or a scenario that's typical of your situation to help develop policy for these things. So that's the end of a quick overview. Many of what these things that we have looked at, we will go into in more detail in specific videos later in the series. Thank you.